Hello there, Mr. Sutton here, bringing you the AB Calculus 515 Extra Practice number 4 solutions on integration by substitution with definite integrals. For this free response problem, we are given the graph of f prime, and they even gave us some areas under the curve, which was kind of nice. This is only defined on 0 to 7, and we're told that f, the original function, is defined for all real numbers and satisfies f of 4 equals 10. Also, we have this random g function that equals 5 minus x squared. Awesome. So we want to find, for our first part here, we want to find the value of the integral from 0 to 7 of f prime of x dx. So basically we're just asking for area under the curve of f prime. So just going from 0 to 7 and keeping in mind that area under the x-axis is going to be considered negative here since we're going from left to right with this integral. We've got 2 plus actually minus 7 and then plus 3 plus 1. So you could leave it like this, or if you wanted to simplify it, let's see here. We've got negative 5 plus 3 is negative 2 plus 1 is negative 1. For this part of the problem, given that f of 4 is 10, they really had to spell it out there, I guess. They want us to write an expression for f of x involving an integral. And then we'll use that to find the absolute min and max of f. Okay, so let's start with our expression for f of x. In general, to find any function value here, we need to start with the value they gave us, which is going to be 10 at the x value 4. And to that we have to add the integral from 4 to x of the f prime function. So the way I'm going to write this is f of x equals 10 plus integral from 4 to x. And here's where I have to be careful. I have to write f prime of t dt. I could use a different letter other than t, but I can't use x because I've already used x up here as my upper limit variable. This dummy variable inside here has a different purpose, so we need to use a completely different variable in order for this to be mathematically legitimate. All right, so now we want to use this to figure out the absolute min and max, and the way we're going to do this is with the candidates test. We have to figure out f of 0 and f of 7. We have to test out the endpoints no matter what. We also have to test out some critical values in between, places where f prime equals 0. So where does f prime equal 0? Well, we're going to equal 0 at x equals 1. So basically anywhere we cross the x-axis with this graph here. Also 4 and 6. I'm hesitating to include this because since there's no sign change in f prime here, this is not going to be a local max or min, so it's not going to be an absolute max or min, but we'll throw it in there because it would take more effort to explain why we're leaving it out. And then we also have to test out, and 7 is also a 0, an x-intercept, but we were going to test it anyway because it's an endpoint, but I'll throw it in there because f prime of x does equal 0 at 7. All right, so testing these things out, let's start with f of 0. f of 0 is going to be 10 plus the integral from 4 to 0 of f prime. So if we're going from 4 back to 0, we're integrating backwards. So all this area that used to be positive is going to be negative and vice versa. So instead of doing plus 2, this area now counts as negative 2. And this area down here that used to be negative, that now counts as positive 7. So f of 0 then is going to be, let's see, 8 plus 7 is 15. Next, we're going to test out f of 1. That's going to be 10, and now we're just going to be doing plus 7 to get from 4 back to 1. So that's 17. Next, let's see here. We had 4 was our next critical value. So that's going to be, well, actually they gave us that. f of 4 is 10, they told us. So no need to do any more work on that one. And then we also need to figure out f of 6 because we didn't write down anything to exclude it, even though we could have. So that's going to be 10 plus this area in here. Since we're going from left to right now, area that looks positive really is positive at this point. So this is going to be 10 plus the area 3, which is 13. And finally, we need f of 7, which is going to be 10 plus 3 plus the 1 here, coming out to 14. So looking at all of these, let's do the absolute min first. So it looks like the smallest value out of all of these candidates is this 10 right here. There's nothing smaller, so that is our absolute min. And then the absolute max, the biggest number, let's see, we got 10, 13, 14's bigger, 15's bigger still, 17 is the biggest of all, so that is our absolute max. For this problem, they want us to find the indefinite integral of g of x d of x. So we're just doing antiderivative, basically, of 5 minus x squared dx. Using the reverse power rule, we've got 5 turning into 5x, and then for x squared, this bumps up to a 3. Dividing by that, we have minus 1/3 x cubed. And here's where they're going to get you. Don't forget the plus c. For this next problem, they want us to figure out the value of the definite integral from 1 to 2 of x f prime of g of x dx. Now, the key here, which will make your life a little bit easier, is if you actually replace the g of x with what it stands for, the 5 minus x squared. Because if we do that, we see that we now have an inner function, and the derivative of that inner function, which involves an x, is elsewhere in this problem. So this is kind of the red flag for using integration by substitution. So I'm going to start that process by letting u equal 5 minus x squared, and then du is going to be negative 2x dx. Dividing by negative 2x, we have du over negative 2x being equivalent to dx. So that takes care of at least this expression here and the dx, and we're hoping this x and this x are going to cancel out in a moment. We still need to turn these limits of integration, though, which are currently x values, into u values. If we're writing du, we need u values for those. So if x equals 1, then what does u equal? Well, that's going to be 5 minus 1 squared, which is 4. And if x equals 2, now we have 5 minus 2 squared, which comes out to 1. So we can rewrite this as the integral from 4 to 1, which is kind of interesting, 4 to 1. And then we have x times f prime of u, and then instead of dx, we have du over negative 2x. X's are going to cancel here, so we have negative 1/2 f prime of u du, integrated from 4 to 1. And this isn't so bad because the antiderivative of f prime is just f. So this is really negative 1/2 times f of u evaluated from 4 to 1. So just applying my fundamental theorem, this is just going to be f of 1 minus f of 4, and we still have that negative 1/2 lingering outside there. And we actually have to plug some numbers into this, though. So we have the negative 1/2, and then f of 1, we actually found this back in part B, but if you forgot what it was, remember f of 4 was 10, and to get f of 1, we just have to add this area in, but we're going backwards, so we're really, instead of using negative 7, we're doing positive 7. So that was 17 for f of 1. And then f of 4, again, they gave us that one. That was 10. So it's 17 minus 10 in there. And this is all constants now, so you could leave it that way, or you can simplify this to negative 7 over 2. For this free response problem, we have Brandon and Chloe riding their bikes for 4 hours along a flat, straight road. Brandon's velocity in miles per hour is given by a differentiable function b, and values of that apparently are in this table up here. So this table is all about Brandon. And then we have Chloe. Chloe's special. She gets a piecewise function for her velocity. Good for you, Chloe. We want to know for part A, how many miles did Chloe travel from time 0 to time 2? So when I'm asking how many miles Chloe traveled, one important question to consider is, did Chloe change directions at all? Because then the displacement and the total distance would be different numbers. Whereas if she doesn't change direction at all, we can just take the displacement and that will be her total miles traveled. So taking a look here, the function we need to use, since we're going from time 0 to 2, is this first branch of our piecewise function, the t times e to the 4 minus t squared. Now looking at this, we see that on the interval from 0 to 2, c of t equals 0 at, well, let's see, if we set each of these individually equal to 0, t equals 0 would be one spot. Can we make e to the 4 minus t squared equal 0 anywhere? We cannot. An exponential function is always going to be positive, so we only equal 0 for the c function at time 0, which is to say basically there are no direction changes on the open interval from 0 to 2, which is good, because that means to find this out, to find out how far Chloe traveled, all we have to do is take her rate of change, her velocity, and integrate that from 0 to 2. So from 0 to 2, the integral of t times e to the 4 minus t squared dt. This will give us Chloe's miles. So that was the first hurdle, is figuring out what we needed to do mathematically. The next hurdle is actually doing it, because this is kind of a tricky one to take the antiderivative of. But one thing that will help us out is we have an inner function here whose derivative, which involves just a t to the first power, is also in this problem. So this is kind of a good candidate for integration by substitution. So let me start that process by letting u equal 4 minus t squared, and then I can write du, the derivative, equals negative 2t dt, and then I need to isolate dt because I'm going to swap that out over here, so I can do du over negative 2t. I also need to get these t values here to be u values instead for my limits of integration. So if t equals 0, then u is going to be 4 minus 0 squared, so 4. And if t equals 2, then t is going to be 0. So now we've done a whole bunch of prep work here. We're going to substitute a bunch of stuff in. So I now have the integral from 4 to 0, which is kind of neat. It's sort of a backwards interval there. We also have a t times e to the u, and then instead of dt, we can replace that with du over negative 2t. So this t and this t down here are going to cancel. We have negative 1/2 e to the u du, evaluated from 4 to 0. Antiderivative of negative 1/2 e to the u is negative 1/2 e to the u. That works out nicely, and we're evaluating that from 4 to 0. So I can yank out that 1/2, and inside of parentheses I've got e to the 0 minus e to the 4th. These are all constants, so I could leave it this way. Or if I really wanted to, I could simplify this, since e to the 0 is just 1, I could simplify this to negative 1/2 plus e to the, there we go, negative 1/2 plus 1/2 e to the 4th. And don't forget the units on this. Chloe's traveling miles, so let's put that over here. For this problem, we want to know if Chloe's speed is increasing or decreasing. So all we have to do here is compare her velocity and her acceleration at time 3. For her velocity, we just have to use the c function, because that's what the c function gives us, Chloe's velocity. Plugging in 3, we're going to use this second rule because 3 is between 2 and 4. So we have 12 minus 3 times 3 minus 3 squared. That's going to be 12 minus 9, which is 3, minus another 9 is negative 6. The important piece to come away with for this is that this is a negative number. Now moving on to the acceleration, for that we need c prime. On the interval from 2 to 4, which is what we need because we're doing c prime of 3, 2 to 4 interval, c prime is going to be negative 3 minus 2t, just using our power rule. And now if I do c prime of 3, we're doing negative 3 minus 2 times 3, so negative 3 minus 6, which is negative 9, also a negative number. We observe that Chloe's velocity and acceleration, c and c prime, have the same sign. They're both negative. Therefore, Chloe's speed is increasing at time 3. For this part of the problem, we want to know if there's a time between 0 and 4 at which Brandon's acceleration equals 2.5 miles per hour squared. So we have a chart here, a table of Brandon's velocity, and we're asking about a value of his acceleration, which is the derivative of velocity. Well, if we're trying to make a leap from a function to the rate of change of that function, the instantaneous rate of change of that function, we're basically trying to use the mean value theorem. So to use this, we need to first establish that the original function is differentiable on the interval that we're involving here. And we said here Brandon's velocity is given by a differentiable function b on the closed interval from 0 to 4. So since b of t is differentiable on the closed interval from 0 to 4, it's continuous on the closed interval from 0 to 4, which is a condition of the NVT, and it's also differentiable on the open interval from 0 to 4. So this covers everything right here, this statement. Since this is the case, it is also going to be the case then that the average rate of change of b of t over 0 to 4 is going to equal the instantaneous rate of change for some value on that interval. So what is the average rate of change from 0 to 4? That's going to be b of 4 minus b of 0 over 4 minus 0. So that's going to be 11 minus 1 over 4 minus 0, or 10 over 4, which comes out to 2.5 miles per hour squared. So then by the MVT, since we have the differentiability and the AROC equals 2.5, the MVT shows that Brandon's acceleration, which is essentially b prime of c, is going to equal 2.5 for some c value on the interval from 0 to 4. For this last part of the problem, we want to know if there's a time between 0 and 2 at which Brandon's velocity is equal to Chloe's velocity. So the key to this one is recognizing that we'll know these velocities are equal if we take one velocity and subtract the other velocity and we end up with a value of 0, because then we'll know we just subtracted something from itself. So that's really where I'm going with what I'm about to do here. So here's my setup for this. Eventually I'm going to want to use the intermediate value theorem to show that the difference between these velocities has to be 0. In order to set that up, I need to establish that this function I'm about to set up is continuous. So I'm going to start by establishing that Brandon's and Chloe's velocities are continuous, and then I'm going to put them together into a bigger and better function that also has to be continuous. So Brandon's velocity, let's look at that first. Brandon's velocity, they said, is differentiable. Therefore, it's continuous because it is differentiable. So that one's an open and shut case. How about Chloe's velocity? The only velocity we care about for Chloe is between 0 and 2. On this interval, we have a polynomial times an exponential. Since those are individually known to be continuous function types, the product of those will also be a continuous function, because again, you're doing a polynomial times an exponential. Okay, so I'm going to define a new function now. I'm going to define this as d of t, which is going to be the difference of Chloe's and Brandon's velocity. Sorry, Brandon, forgot your name. So I'm going to say d of t equals c of t minus b of t. And what I'm about to do, it doesn't really matter what order you subtract these in. I just picked an order and went with it. So this function now, because it is the difference of two functions that are continuous, this function will also be continuous on the interval from 0 to 2. And that's very important because I'm about to use the IVT to talk about values that this function has to equal. Specifically, I want to show that d of t must take on a value of 0 between 0 and 2. Because if d of t is 0, that means that c of t and b of t had to be the same value at some point. So let's take a look at the value of d of t at 0 and also d of 2. And hopefully we show that 0 is sandwiched between those two output values. So doing d of 0 first, that's c of 0 minus b of 0. C of 0, that's just going to be 0 times all this e stuff, which comes out to 0 for the c function. B of 0 is 1, so we're basically doing 0 minus 1, which is negative 1. Now negative 1 is less than 0, which that's a good start. So I'm hoping now that d of 2 is going to be some number that's greater than 0. So let's figure this out. D of 2, that's c of 2 minus b of 2. Now c of 2, that's going to be 2 times e to the 0 essentially, which is just 2. B of 2 up here, that's 1.5. So d of 2 then is going to be 2 minus 1.5, which is 0.5. And again, I'm establishing that that is specifically d of 2. That's how I got this random 0.5 number. Since I have a continuous function on 0 to 2, and I've shown that the value I'm looking for is sandwiched between the beginning and ending values, by the IVT we are guaranteed that d of t equals 0 for some c value on 0 to 2. Because d of t equals 0 somewhere on 0 to 2, it follows that b of t equals c of t, or vice versa, for some c value on 0 to 2. And that basically proves what they were asking us to prove, which was that Brandon's velocity and Chloe's velocity have to equal each other somewhere because their difference is 0 somewhere on this interval.